Evaluating limits at infinity. The formal definition of a limit not at infinity, as x approaches a, we gave here, which we didn't bother going through because it's not required for pre-calc, and the epsilon definition does take a bit of a time to understand. But this one should make a little more sense, that the limit as x approaches infinity is c if for any value, for any positive value, you can take any x value greater than some point so that all of the y coordinates are within a certain band. So the idea is that there's some sort of asymptote, and that doesn't actually mean that it can't cross it, but if you want to say somewhere in here you can pick a point after which all of the points are in this band, and then if you want to make a smaller band, you can say all of the points after this point will be in that smaller band, and it gets closer and closer to whatever the limit is. So the informal definition, it's a way of classifying the end behavior based on what value the function approaches. If it approaches something, if we say limit as x goes to infinity of f of x equals 3, then we say the limit converges. And if it does not, if we say it goes to infinity, then we say it diverges. And that's something, for example, if we take the limit of e to the x as x goes to infinity. Well, this is an exponential function. It just gets bigger and bigger. That looks like this, and it clearly diverges at positive infinity, but it converges at negative infinity. It converges to 0. So here's some examples. This is a convergent limit would be something like, let's say, a rational function with this asymptote. It converges there. So that's an example of a convergent limit. Here, this is something like y equals x has a limit that goes to positive infinity. If I take something like that, that would have a limit of negative infinity if this were, say, y equals negative square root of x. If I plug in a really large value of x, this will still be a very negative number. And if the limit does not exist, then that's something along the lines of sine. So something like sine, it doesn't go to infinity, it doesn't go to negative infinity, and it also doesn't get closer to 0 or 1 at any value. It just oscillates. Now, if it were getting smaller, then it could converge. Just because it oscillates doesn't mean that it that doesn't mean it diverges. If you have that, this would still count as having a limit. This one does not have a limit because it never gets closer to any particular value. So polynomials, we talk about this in terms of the end behavior. So something like if we had y equals x cubed, that has positive end behavior and negative end behavior, and we describe that as the limit as x goes to infinity of x cubed is infinity. Exponential functions. Typically, exponential functions, something like y equals e to the x, looks like this, with one of the sides converging to the asymptote, and the other side diverging to infinity. Logarithms aren't defined at negative infinity. They're not defined for negative numbers, so there's no end behavior on the left, but the end behavior on the right is that they diverge. So the limit of natural log of x as x goes to infinity is also infinity. Trigonometric ones typically do not exist for the reason mentioned here. It typically oscillates. And rational functions at asymptotes. So if you imagine plugging in a really large positive number here, all that's going to matter are going to be the highest exponent. everything else will be so small that it won't make a difference. So I think of this as crossing out everything else. Then we can divide 3x squared by x squared, and we will get 3. And 3 is the limit at infinity. This is the same way that we found that the asymptote of this function would be y equals 3. Over here, well, the only thing that's going to matter is the highest exponent. And there's nothing in the denominator that competes with that highest exponent. So because the highest exponent is in the numerator, I would say that this diverges to infinity. In other words, because x squared is being divided by 0x squared, I think of this as 1 over 0, which is not equal to, but approaches infinity. Here, the limit as x goes to infinity of e to the x over x to the fourth minus 1. Well, e to the x grows really fast. X to the fourth grows fast, but e to the x grows a lot faster. So e to the x over x to the fourth, this is going to be approaching infinity. If I plug in, say, 1,000, e to the 1,000 over 1,000 to the fourth, this is going to be really big because this is way bigger than that. Minus 1 isn't going to make a difference for the limit at infinity because it's still going to infinity. So because exponential functions grow so much faster than polynomial functions, that's why we say that the limit is infinity. Here, however, because this is getting closer and closer to, because the denominator of the exponent is getting closer and closer to 0, this is approaching, say, this is something like e to the 1 over that, which is like having a really large exponent. A very negative exponent because it was negative infinity. So because it has a very negative exponent, this is something like e to the negative 10,000. And as this 10,000 becomes more and more negative because of that, we have, I'm sorry, as we plug that in, this gets closer and closer to 0, because we're plugging in more and more negative numbers in for x, which means that this is getting closer to negative 1 over 10,000 or negative 0.001. And as we make x bigger, 1 over x gets smaller. And when 1 over x gets smaller, this is getting closer and closer to 0. So the whole thing is getting closer and closer to e to the 0, which is 1. So the limit here is 1.